Okay, hello everyone. We are back with chapter 5. We're going to continue our exploration of addition reactions to alkenes. We're going to start with hydration, which is the addition of water across the double bond, and then move into halogenation and halogenation and hydrogenation, and also hydroboration. So what we're going to do is start with hydration, which you'll find has a pretty similar mechanism, not identical, but similar to hydrohalogenation in that it goes through a carbocation. So let's start by sharing my iPad. So hydration is the addition of water. What we know is that an alkene will not react with pure water all by itself. I have to have a very small amount of a strong acid catalyst. This catalyst is critical. Without this, there is no reaction. When I put that catalyst in there, I end up with the addition of hydrogen and OH adding across the double bond, where I just put on this hydrogen and this OH, and I end up with an alcohol. Now this is a symmetric alkene, so regiochemistry doesn't matter. But just like with hydrohalogenation, if I have an unsymmetrical alkene, I am going to follow Markovnikov's rule when I do this. Okay, when I do these reactions, I am going to uphold Markovnikov's rule. So here's some examples. If we look on this one here, remember, I always have two choices. I could do this way, or I can add this way. And this is going to be my most substituted carbon. And this is my least substituted carbon. This has two hydrogens. This only has one hydrogen. Remember, the hydrogen is going to add to the carbon that has more hydrogen, or the least substituted carbon. And that is going to be Markovnikov's rule. Markovnikov's rule. So notice that would mean that this carbon is going to get that hydrogen, and this carbon is going to get the OH. And if you notice, that's what I see here. I get 2-propanol, and I don't get the other one. But remember, this is also going to go through a carbocation mechanism. I don't know what I am pressing on. Hello. To make that keep going in and out, but oh well. I must be pressing on something. Move my computer a little bit. Again, if I look at this example, which is over here, I have CH3, CH3, CHH. This carbon has 2 hydrogens. This carbon only has 0 hydrogens. So my alcohol, or my hydrogen, is going to want to add to this side. So I'm going to add in this direction, and then I'm going to end up with this. So both of these are the Markovnikov product. Just for yucks, if I'm gonna make the other product, this would be the minor product that does not form. And then if I do it on this one, I would end up with the hydrogen there and the alcohol there. This would also be minor and does not form. Because both of these products are going to go through the primary carbocation, which is not stable. So again, if we look at this, I have no hydrogens on that carbon and 2 hydrogens on that carbon. So the hydrogen is going to attach there based on Markovnikov's rule. Of those 2 potential products, right, I'm going to get this one, which is that Markovnikov addition product. So the OH ends up on the least substituted carbon, which is this guy, and the hydrogen ends up on the most substituted carbon, which is that guy. Notice I can also write this as this compound down here. Those are identical connectivity, so they are the same structure. If you named it, you would see that you get 2-methyl-2-propanol if you put that hydrogen on there and sort of represent that CH3 as a methyl group. All right, so let's look at the mechanisms. Mechanisms are always the most fascinating things. The first step is to add a proton. But let me show you what happens first. So water is present, and water is actually going to add, it's going to protonate using the acid. So this is whatever acid is there. Now remember, water can be protonated. It can act as a base, which it's doing right here. And what I get is this hydronium ion concentration, which remember is the species that's actually formed when acid and water react together. I get H3O plus I get whatever counter ion I had of the acid. So this H3O plus that's formed from this acid reacting with water is the electrophile in this first step, which is adding a proton. This is actually what's adding the proton. The acid reacts with the water, and it's this H3O plus or hydronium ion, right? This is a hydronium ion that reacts with the electrophile, or with the nucleophile. This is the nucleophile. Remember, this is electron rich. This is an electrophile. This is an electron poor species. These electrons are going to attack that hydrogen, and then these electrons are going to end up on oxygen. And notice that I just made water, but I have, I'm going to draw this out. This secondary carbocation. This secondary carbocation is formed in this first step. Now, the other carbocation that can form, right, is if that hydrogen adds to the other side. So if hydrogen sort of ends up where the hydrogen ends on that carbon, what I'm going to get then is what am I going to get? I'm going to get this guy. Right? So this is the one carbocation. Remember, I can also get a second carbocation, but this is a primary carbocation. So this is very unstable and doesn't form. This is the carbocation that actually forms in this particular reaction. So I'm just showing that to remember that we talked about how Markovnikov's rule actually directs the stereochemistry, because when I form those two separate, those two different carbocations, from attaching the hydrogen to the two different carbons in the double bond, I am going to assess those two carbocations, and if there's a marked differential in their stability, the less stable carbocation isn't going to form. And we know that primary carbocations are particularly unstable. So if I have a primary carbocation versus a secondary or a tertiary, I'm only going to form the secondary or the tertiary carbocation. And again, this is all the reason why we observe Markovnikov's rule in hydrohalogenation and also in this hydration. There is this step, though, where the acid forms H3O plus. That is sort of an additional requirement. If I don't have this H3O plus present, I'm not going to form the carbocation. That's why I need acid in this reaction, because if I don't have it, I'm not going to form a carbocation. The water itself is not electrophilic enough in order for that double bond to react with it. It needs to be, the water needs to be made into an electrophile, which is positively charged, right? So that's electron poor, and that happens by protonating water with the acid that's present. So the next step is pretty much similar. I'm going to react the nucleophile and the electrophile, and I'm going to form a new covalent bond. So these two electrons actually end up reacting with the carbon that bears the positive charge. And this is a fast step. Remember, the slow step is always formation of the carbocation. Now this here is an oxonium ion, which is basically a protonated alcohol, right? I have the two hydrogens of water. It's these electrons that are acting as a nucleophile. Now this carbocation is acting as the electrophile. So in this, the initial product of this step is the formation of this oxygen-carbon bond. Those hydrogens are still there. And if I assign the formal charge, 1, 2, and then half the bonding, 3, 4, 5, this ends up being a positively charged oxonium ion. So that's when I have that positive charge on an oxygen, and it's an oxonium, like the hydronium, but now this is oxonium. Now, I can't leave this alone, because I'm not going to have this positively charged oxonium ion as my product. So my third step is to take a proton away, which is going to give me the neutral alcohol. So water is acting as a base, basically, and those electrons are going to come and attack that hydrogen. Those electrons go on the alcohol. What I end up now is the neutral alcohol as my product, and I've regenerated, right? I've regenerated the H3O plus catalyst. So it's this depronation that's another step compared to the mechanism of the hydrohalogenation. And again, you have to show these various steps when I ask you to draw a mechanism. So you have to be very particular on how your bonds are forming and how your bonds are breaking. So again, these electrons end up as the lone pair. And these electrons end up forming this OH bond. All right, so here is another problem. Account for the fact that the acid catalyzed hydration of alkenes can be used to prepare both secondary and tertiary alcohols, but with the exception of ethanol, it cannot be used to prepare primary alcohols. Oh, that sounds like a discussion question. So let's think about this. If I have a double bond, right, what I'm going to have here is this combination is going to give me hydronium. Now, I can go one of two ways. So if I look at this, I can go where my bond is going to come this way. And what I'm going to end up with there is a secondary carbocation, right? When I go through this mechanism, I'm not going to count those two steps. I'm going to end up with this guy, okay? So notice this is a secondary carbocation. Now, if I do it the other way, and I form the other carbocation, what I'm going to get is this, and I'm going to end up with this primary carbocation. Well, notice that any time I form a primary alcohol, this is going to come through a primary carbocation, which is not stable and will not form. So this is unstable. I'm always going to form the secondary or tertiary carbocation, which gives me the secondary and tertiary alcohols. I can use ethanol to form primary alcohols, but that's a special case. Okay, hopefully that makes sense. Here we go. Draw the structural formula of an alkene that undergoes acid catalyzed hydration to give each alcohol as the major product. More than one alkene may give each alcohol as the major product. So what I have to think about is that this is the carbon that has my OH. So I could have, remember, my carbon-carbon double bond is two adjacent carbons. So I could have this carbon as part of the double bond, or this carbon as part of the double bond, or this carbon as part of the double bond. So if I get rid of this sequence, right, and I'm going backwards, I'm going to get the double bond, and then I have that, right, I'm making the double bond in between these two carbons here. I have another choice, which is the orange choice, and I could get rid of this water, and then I would have this. Now these are actually identical, so that doesn't give me a separate product. The red choice and the orange choice give me the same product. So these are equivalent. They're the same product. Okay, so really I only have one choice there. But I do have another choice here where I'm going to get rid of that water. And if I do that, what I'm going to get is this, here's my double bond, and then I'm going to get that. So I have So really I have two choices. I'm going to have those two alkenes that when they react with water, I'm going to get that product that we started with. So this is what I have to do. I have to figure out what double bond came to give this product that's the alcohol. And remember that my double bond is always going to be connected carbons. They're adjacent to one another. So if I want to do that here on this one, here's my carbon that has a double bond. Notice I could make a double bond there, or there, or there. Now, what you should know is these two positions are equivalent. There's symmetry there. So really I only have the top choice and then to one side on the ring. It doesn't matter if I put it on the left or the right, I'm still gonna get the same answers. So I'm going to get this guy, or I'm going to get this guy, which is going to give me that alcohol if I add water to it. And if I put this double bond on this other side, they're equivalent. So I really only have one position, two position that gives me the alkenes. So let's look at this guy. Here's my alcohol. This and this are the same. So I have this position or this position that could give me the double bond. So I'm going to take off the hydrogen that's there, or I'm going to take off the hydrogen that's there, and what I'm going to end up with is that guy. Now, hopefully you'll notice that when I look at this carbon, I have choice 1 to give up a hydrogen, choice 2 to give up a hydrogen, or choice 3. Those are not equivalent, right? This carbon here and this carbon are not equivalent because this has that methyl group there. So there's actually 3 choices. I could get rid of this water molecule. And what I'm going to end up with is this. I could get rid of this water molecule, and what I'm going to end up with is this, or I could get rid of this water molecule, and what I'm going to end up with there is that alkene. So this is a little tricky. You have to play around with it. You have to really think about what's happening as I go forward by going reverse, right? So we're not going to get into synthesis too much, but we do get into it a little bit. And you will notice that when we do talk about synthesis, that we are going to have to start thinking backwards and forwards at the same time. So it's a really difficult skill to master. And in this class, we don't go in too depth, but we will talk about it a little bit. Here's another problem. If I treat 2-methylpropene with methanol in the presence of an acid catalyst, I'm getting tert-butyl methyl ether. This is just an aside. At one time, this compound was added to a gasoline to increase octane writing. Blah, 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 blah. I don't care about any of that. What I want is a mechanism for this reaction. So what I'm gonna do is, notice I have acid. What can happen in acid is that I can go, I don't leave myself much space. I could have CH3OH. This is an alcohol that's very similar in structure to water. And this is my acid, and I'm just gonna leave this generically, right? This is partial positive, this is partial minus. So my alcohol is gonna protonate just like water did, and I'm gonna form this oxonium ion, which is very electrophilic. And I'm just gonna get A minus. So that is the species that is gonna react with my alkene. So this now is my electrophile, because it's electron poor. And it's electron poor because I have that positive charge. So now one of these double bonds is going to go ahead and attack this hydrogen. I'm going to have to obey Markovnikov's rule here, right? My OH, right, this is what I'm adding to the double bond. And I'm going to add the hydrogen to this carbon, which has the 2 hydrogens, not to the other one, because that'll give me the most stable carbocation, because this reaction is part of this hydration. It's just a little twist, because now instead of water adding, I've got an alcohol, which is very similar in structure. So this comes out, and then I regenerate the water. And what I get is this tertiary carbocation. Now this tertiary carbocation is really, really stable. Notice if I had added the hydrogen on that one, I'd get a primary carbocation, and that would be unstable. So I don't even bother showing that, because I know that this carbon is this carbon in the product. So I'm going to draw the mechanism that gives me that product. Now, here's the thing. I'm going to have another molecule of methanol come in. Now remember, this is the electrophile, and this is a nucleophile. So this is going to come in, and what I'm going to form is that oxonium ion. Stop. Which is very similar to what I did before. But notice I have this methyl group because that's part of the nucleophile. And then my water is going to come in and get rid of that hydrogen and then give me the product. So I do have that extra step. I'm going to protonate the alcohol first to form that initial electrophile. Then my double bond electrons are coming out, acting as the nucleophile, right? This is going to be the nucleophile because it's electron rich, and it's going to attack that hydrogen. That's going to give me the tertiary carbocation, which then forms a new covalent bond by the reaction with a nucleophile and an electrophile. And then when I get this oxonium ion, I'm actually going to form, this is my intermediate, it's not my final product. My final product needs to have that deprotonation of the hydrogen, right, in order to give me the neutral ether in this case. So notice that the piece that I'm adding is this OCH3, which is from the methanol minus the hydrogen. And that's what I'm adding at this step. And also here, that's where I get that OCH3 in these different things. And I didn't put this. This has got the OCH3 as well, because this is my initial OCH3. This is my initial, OCH3. So you want to keep track of all your atoms. In order to make sure that you draw the right products when you're drawing these mechanisms. All right, I'm going to stop here, and then we are going to come back and cover some more Chapter 5 reactions. Okay, I will be back in a bit.